Okay, welcome to the second half of lecture two. I apologize that I am posting this so close to our second lecture. And in fact, maybe on Tuesday, I'll have a discussion with all of you to see if this format is actually working for you. I have a feeling that maybe live lectures will be more helpful, especially because I want to make sure that all of you are kind of understanding the concepts as I present them. And then maybe I can make videos of R coding. I don't know, that it's pretty mundane. I'm sure they will be incredibly fun to watch. So not really. So maybe that might not be the best approach, but we can talk about it a bit more on Tuesday. So anyway, let's just get started. Let's kind of pick up where we left off. So remember at the end of lecture 2A, we looked at populations, the entire population, so adults in San Diego, and then we took samples from that population and estimated the distribution of males versus females in those samples. And in most cases, we don't know what the true parameter, so the truth, what the truth is, and that's what we're trying to infer with our samples. So how do we go about figuring out whether our sample means, for example, our sample statistics are different from the population parameters? So really the aim is, is what we're observing, is it rare or is it common in the population from which we're drawing our samples? So to start to get at that, we're going to talk about sampling distributions. So remember, when we perform an experiment, we're manipulating an independent variable, and that's something that doesn't change. That's something that we act on, and then we're hoping that we will change the value then of a dependent variable. So let's say we're interested, we have a sample of 20 individuals and we want to give them a training regimen to see if it has an effect on their, let's say, their resting heart rate. So maybe this independent variable, we're interested in, we have a sample of men and women. And so the independent variable might be sex, for example. And then we, intervene with this training regimen, and then we see if there's a change. And then, further down the road, we might be able to ask, is there a change? Is there a difference in the change between those men and women in our sample? So ideally, if the change is large, our sample statistics, so for example, the mean, so maybe like the average change in the resting heart rate, should be significantly different from what we would expect due to sampling error. And that's just random chance. So remember, ideally we would take these simple random samples from our population, but that's not always the case. And so just by chance, our samples are always going to be a little bit different from our population from which we've drawn the sample. Okay, so the first thing we need to do is estimate what values for our sample statistic would be common or rare. And so here in this figure, we have what's called a probability distribution. And remember, probability distribution is a lot like a histogram of our statistics, of the frequencies of our statistic. So for example, the mean. And in this probability distribution is very similar to a histogram where if we can imagine these are like bars under this curve here, correspond to the relative frequency of an observation. In this case, it's the probability. So this white area actually corresponds to 95% of that area under that curve. The textbook talks a little bit about probability distribution and probability density. And I'll try not to, I'll just cover it very briefly. I think even the textbook said, let's discuss it, but it's not something, really important unless you start getting into more advanced statistics. But this is a curve that we will revisit. And Dr. Armenta, I believe, talked about it a little bit in his first lecture when he started to introduce hypothesis testing, but we're going to see this curve when we start to talk a little bit more about specific hypothesis tests. So if you can imagine, the area under this curve corresponds to a value of 1. So remember, probability ranges from 0 to 1. And this central, the center here corresponds to the mean. And in a standardized normal distribution, there is a mean of 0 and a standard deviation of 1. And so what this is saying is that 95% of 95% of this curve falls within a range of the mean plus or minus almost 2 standard deviations. Okay, so here would correspond to the most common common occurrences, and then out here in the tails, that corresponds to the less common or rare outcomes. Okay, so that might not be super clear, but it'll become more clear when we start to talk about specific hypothesis tests. Okay, so what is a sampling distribution? And this is where we start to be able to estimate the population parameters and then compare our statistic to this unknown population parameter. So the sampling distribution of a statistic is the distribution of all possible values taken by the statistic when all possible samples of a fixed size n are taken from the population. So it's just a theoretical idea, right? In truth, we don't take, infinite number of samples from a population, calculate, for example, the mean, so our sample statistic in this case being the mean, and then calculate the means for all those infinite samples, right? In truth, we can't do that. So it is just a theoretical idea. But this will be very helpful as you'll see later on. So the sampling distribution of a statistic is the probability distribution of that statistic. So if we were to take many random samples of a given size n from a population that has a mean mu and a standard deviation sigma, some samples will be above the population mean and some will be below, and that makes up our sampling distribution. So, okay, so let me kind of tie it back. Remember, in that last half of the first section of lecture 2, we were drawing 2 samples from the entire adult population of San Diego. And if you remember, the distribution of male female was different in each of those samples, and it was different from the population values, right? And so that's all that's saying, is sometimes the mean will come in above, sometimes it'll be below, sometimes it will be exactly what the population mean is. So before we can compare our sample mean with the population mean, we need to know 2 things. Are the sample means normally distributed? And what is the standard amount which sample means will deviate from the population mean? Okay, so if we know the standard deviation from the sample means, and those means are normally distributed, we will be able to use the Z distribution, which is actually what I presented in that first slide, to calculate proportions for any sample mean. And this is what will tell us if the sample statistics value is common or rare. So remember, in that probability distribution that we saw in the first slide, that central area, those correspond to common values. And then in the tail ends, those correspond to rare values. Okay, so let's talk about the sampling distribution of the mean. So the mean it comes up a lot because it's one of the most common statistics that we calculate. So any population of interest contains a potentially enormous number of samples of size n. Okay, so each sample with a size of n number of individuals or observations. The sampling distribution of the mean is a probability distribution of means for all possible random samples of a given size from the population. So if we were to take samples from the population, calculate its mean, take another sample from the population, calculate its mean, That sampling distribution of the mean is just the distribution of all those means for all those samples. So it's essentially a histogram of all sample means for a population, and it shows the relative frequency. And it's also known as the distribution of sample means. So this is a great figure here that depicts this. So this purple line corresponds to the actual population. And in this case, it corresponds to 4,000 students. So let's say the population of interest is 4,000 students, and they are all the students at a local community college, for example, okay? And so the actual population mean, mu, is for their average weight is 134.21 pounds. Okay, now let's say we take, and this is the pink line here, we take a sample of 200 students. And you can see this curve isn't very normal, right? It's a little bit skewed, and the mean is pretty far away from the population mean. So the mean from our sample of 200 students is 135 pounds. Okay. But now let's say we take another sample of 200 students and another sample for a total of 20 samples of 200 students from this entire population. And then we plot the distribution of those means. Now look at this curve. It's a little bit more, it looks pretty normal, right? Normally distributed. It's a little bit shifted away from the true population mean of 134.2 pounds. But if you look at this mean, it's pretty close, right? It's closer than this just initial single sample of 200 students. Now in the 20 samples of 200 students, when we take the mean of those means, we get 134.55 pounds. So it's closer to the population mean, and the distribution looks a lot more normal than the distribution for just that single sample of 200 students. Okay, so here's another way to look at this. Instead of just, we'll kind of work our way through it and show you that this actually happens. So let's say, for example, we have a miniature population. Okay, we have a miniature population, and that population consists of 4 values, 2, 3, 4, or 5. Okay, so there's just 4 possible values, each with a frequency of 1, and the true population mean for that population is 3.5. Okay, so that's just the average of 2, 3, 4, and 5. So now let's create a sampling distribution for samples of 2 observations. So what we're going to do is take a sample from that miniature population, and that sample size is going to be 2. And then we're going to take the means of all of those samples of 2, and then we're going to itemize all those possible samples, and then we're going to calculate the mean for all of them, and then in the next slide we'll plot all that and see what happens. Okay, so just a quick note, all possible outcomes for these samples is called our sample space. Okay, so I know this is a busy slide. I'm just going to take a pause here. Okay, so I'm going to try to break this down. All right, so remember we had a population, and that population had one of each of these 4 values, 2, 3, 4, 5. Okay, so these are the values on the x-axis here, and this is just the frequency. So it's just one of each of these values, okay? On the left-hand side, we see all 16 possible samples of 2 taken from this population, okay? So in the first sample, we've taken from our population of 4, 2 observations. And here we've randomly picked 2 twice. Okay, and so this assumes that we've picked out an observation, we've put it back. Let's say it's like 4 marbles, okay? And each one have a number, 1, 2, 3, 4. 2, 3, 4, 5. And we take out a marble, write down the number, we get a 2, and then we put the marble back, and then we take out the marble again, and we get another 2. Okay, and this is called sampling with replacement. Okay, then let's say we take another sample, we take the number out, we get the number 2, we put it back in, and then we take another one out and we get the number 3. Okay, and so then the sample mean here is 2.5. All right, so and so on and so forth until we get to this very last sample of 2. We take out a number, we get 5, we put it back in, we take out another number, and we get 5 again. Okay, so the sample mean here is 5. Okay, so these are all the 16 possible outcomes that we can draw from our population. And each one of these has a probability of occurring 1/16 of the time. Okay, so now if we take all of these sample means and then we create a histogram of those sample means, now you can see this is the probability of us getting a sample mean of 2, and that's 1/16. And then this is the probability of getting a sample mean of 2.5, and that's 2/16, okay? And we've plotted this all the way up to a sample mean of 5. Remember, the true population mean is 3.5. And as it turns out, it's also the most common mean in our sampling distribution, right? So look at this. That occurs 4/16 or 1/4 of the time. Okay, and it's also the most common. And also note that these two are rare at the ends, okay? But this is what I want to draw your attention to. So it turns out that the sampling, sorry, the mean of that sampling distribution is equal to the population mean. And this is a really cool feature, and I'll introduce a theorem later on that that's very central to frequentist statistics. Okay. All right, so one thing, with some of the features of this sampling distribution is that as the sample size increases, the variability in our sample means decreases. So this just means, okay, in our example, we took, we just had a miniature population of 4, and we took sample sizes of 2. But let's say we had a population of interest of 1 million people. And if our sample size, so let's say we take a sample of 1,000 people versus a sample size of 10, the variability in that sample of 1,000 people will be less than our the variability in a sample of 10 people, okay? And then the likelihood of extreme means is also greatly reduced. So if we had a population of 1 million and then we plotted the distribution of sample means for sample sizes of 2, you can see it's pretty spread out here, right? The sampling distribution is pretty spread out. But if we were to increase that sample size, so we start to take increasing numbers of individuals, so now all the way to a sample size of 120 people from that population of 1 million people, and we take the mean of each sample of 120 people and plot the means here, now you see that the variability is greatly reduced. And even, you can't see it, but there still is a chance of values occurring out here, but the likelihood of that occurring is much, much rare. Okay, so now let's introduce, so now we've talked about the mean of the sampling distribution, or the sampling distribution of the mean visually. Okay, now let's talk about variability, right? So in a sample statistic, we talked about the mean, but also the measure of variability being very important, or standard deviation. So just as in our single sample, that was important, it's also important for our sampling distribution. So the standard deviation for our sampling distribution is referred to as the standard error. Okay, and the standard error of the mean is just a special type of standard deviation, and that measures the variability in the sample distribution of sample means. Okay, and this is just the equation for that. Okay, so the standard error is equal to the standard deviation of the population, that's denoted by sigma, divided by the square root of the number of observations in our sample. It is the standard that describes the amount by which sample means deviate from the mean of the sampling distribution or the population mean. Remember, those are equal. Errors refer to the fact that most random samples are not exact replicas of the population. And again, with larger sample sizes, sample means cluster more closely about the mean of the sampling distribution and the mean of the population. And that allows us to make more precise generalizations from the sample to the population. So here's some characteristics of the sampling distribution. The mean of the sampling distribution is the same as the mean of the population. So remember in our little experiment with a miniature population that had a mean of 3.5, and then when we took the mean of the sampling distribution, that was also 3.5. And then again, as the sample size increases, variability of the sample means decreases. Here's another key. The sampling distribution is normally distributed, and it's normal even if the population isn't normally distributed, but the sample sizes are sufficiently large. And then it's also normal if the population itself is normally distributed. Okay, so here is visually is showing you that last point, where even non-normal distributions will produce a normally distributed sampling distribution of the mean, provided that the sample size is large enough. So we see here when we have a very small sample size that we've drawn from our population and then plot the sampling distribution of those sample means, you see that we have a non-normal distribution. But as our sample size increases, it converges into a normal distribution. And all of this is getting at that theorem that I referred to earlier, the central limit theorem. Okay, so this states, if the population distribution has a mean mu and a standard deviation sigma, then the sampling distribution of the mean also has mean, this should be x bar, but it is equivalent to the population mean. And the standard error of the mean is denoted by this equation here. And then regardless of the shape of the population, when the sample size is sufficiently large, so as n approaches infinity, the shape of the sampling distribution of the mean approximates a normal curve. This is from Dr. Armenta's slides, and I thought it was really funny because I think maybe not so much anymore, but at some point these Ryan Gosling memes were very popular. So, you know, hey girl, do you ever wonder what life would be like without the central limit theorem? And I don't know, like a lot of statistics rely on the central limit theorem. And so I'm not sure what life would be like. Probably not have a job. Okay, probability and inference. All right, so notice how we've moved from the population values to sample values and then back again to the population values. Okay, so these are the population values. This is our sample. This is our sample values. Okay, but if we have many samples, if we're working from many samples, this has given us a basis, and it's rooted in probability theory for generalizing back to the population. Okay, so here we see this is a sampling distribution, and it has a mean that is equivalent to the population mean, and then a standard deviation of that mean, or the standard error of the mean, sigma sub x bar. Okay, and everything is still based on empirical observations, but it takes advantage of this tendency toward the normal distribution in nature. So in summary, what is the sampling distribution? It's just all possible random samples of a given size from some population, and then looking at the distribution of a statistic from each of those samples. So for example, the mean. So sampling distribution of the mean would just be a distribution of means from all possible random samples of a given size from some population. And the central limit theorem states that samples of a sufficient size will be approximately normal regardless of the population distribution. Okay, so one of the assumptions in a lot of our tests is that our population has a normal distribution. So some of the things that we need to do before we move on to our analysis and we run hypothesis tests or run our models is we need to make sure that some of these assumptions are met. And one of this is the assumption of normality. So what are some tests that we can use to test normality and make sure that the analyses we are conducting is the appropriate one? A lot of tests that we do and a lot of models rely on this assumption of normality. And so the assumption for parametric tests is that data is normal. And the typical data that we would use or analyze in this way using parametric tests would be ratio or interval data. And then the usual central measure, right? So the measure of central tendency is the mean. Okay, so how do we test normality? How do we test that our population distribution is normal? So we can check the significance of skewness and kurtosis. So if you remember, skewness is when a distribution is not normal, and it might be pulled to the right and be right or positive skewed, or it might be pulled to the left and be left or negative skewed. And then kurtosis refers to the heaviness of the tails. If skewness and kurtosis are both non-significant, then we can conclude that the data is normal. What happens if skewness is significant, but kurtosis is not, or vice versa? So let's use, we can introduce introduce some tests that we can use to test normality. So we can use the Kolmogorov-Smirnov test or the Shapiro-Wilk test. And let's go through those. Okay, so tests for normality calculate the probability that the sample was drawn from a normal population, a normally distributed population. So the null hypothesis in this case is that the sample data are not significantly different than a normal population. The alternative hypothesis is the sample data are significantly different than a normal population. So when we're testing for normality, we're not really looking for a difference. We're just trying to see if our data set was drawn from a normal population. So in effect, we want to see if we want our data to be no different than normal, right? We want our data to have been drawn from a normally distributed population. So we actually, in this case, want to accept the null hypothesis. Right? In most cases, I think people are more excited when they reject the null hypothesis because they want to see a difference in their data, right? They want to see a change, that some intervention has made a difference. But in this case, we actually want to accept the null hypothesis. Okay, so two normality tests that we could use are the Kolmogorov-Smirnov tests, but this is not sensitive to problems in the tails of our distribution. And it's typically used for data sets larger than 50, but less than 200. On the other hand, the Shapiro-Wilks test doesn't work well, actually works best for data sets that are less than 50, but it can be used with larger data sets. However, it doesn't work well if several values in the data set are the same. So if you have ties. Another way that we can test normality visually is by plotting a QQ plot. And that's just a scatter plot created by plotting two sets of quantiles against one another. So if both sets of quantiles came from the same distribution, then we should see the points forming a line that's roughly straight. Okay, so what's an example of that? Here on the y-axis, we have the expected normal, okay? So remember, in a standard normal distribution, there's a mean of 0 and a standard deviation of 1. So we're going to plot our observed values against that expected normal. And you can see here that our observed values don't really fall along that line. And so we conclude that we have non-normal data. On the other hand, this right-hand side, when we plot our observed data against this expected normal, you can see that the points actually fall pretty closely to that line. And so then we conclude that our data was drawn from a normally distributed population. Points that are closer to the straight line correspond to normally distributed data. So in lecture one, I think someone asked the question about a significant p-value in a small sample, and Dr. Armenta started to talk about how in large samples, we tend to, oftentimes find significant p-values just because of the nature of the size of the sample. So this kind of gets at that, where normality statistics are not reliable for large samples because so here, significance tests for normality should not be used for these large samples because they are likely to be significant, even when they skew and the kurtosis are not too different from normal. So another thing that we need to do with our data is to test for outliers. So remember, the mean is very much affected by outliers, right? The median, not so much, but remember when we looked at our skewed distributions, we could see that the mean in a right or positive skewed distribution was pulled to the right, and then the opposite happening where if there was a left or negative skew, the mean was pulled to the left. So it is affected by outliers. So we also need to test for that in our data. So what exactly is an outlier? It's just a data point that is unusual or unexpected. And how do we detect that? So most of the behavioral variables are normally distributed. So therefore, if a random sample is drawn, then any score that lies outside of 3 or 2 standard deviations from the mean is considered an outlier. So for example, if the mean is 40 and the standard deviation is 5, then any value outside of that range less than 30 or greater than 50, right? So that's 2 standard deviations from that mean of 40, or outside the range of less than 25 or greater than 55. So that corresponds to 3 standard deviations away from the mean. Those observations might be outliers. And how do we look at that? Okay, so one way we can do that visually is by plotting a box plot. So let's look at what the box plot is actually doing. So, so for a box plot, so this is using SPSS, which I think some of you have used before, but we can also use R to plot a box plot. So what these correspond to are the minimum and the maximum values in our sample. Okay, and this heavy line in the middle corresponds to the median, and then the edges of the box correspond to the first quartile and the third quartile. Okay, and if you remember, the difference between the third and the first quartile is called the interquartile range, and that's just the middle 50% of our values in our sample. This is a normal distribution, right? Everything is centered. The left-hand side, however, depicts a skewed distribution. So if you look here, our median is pulled down here, very close to the first quartile and very close to our minimum value. And then up here, we see that values 4 and 16, or I'm sorry, not the values, the observations 4 and 16 are outliers. So in SPSS, what it will do is it will actually plot the outliers this way. So that was one way we can visually detect outliers. Another way through actual statistical testing to detect outliers is through the Grubbs outlier test. So this is just the test statistic for if we want to detect an observation that is greater than the mean. And then this is the test statistic if we want to look at something that, an observation that is less than the mean. Okay, where x sub max and x sub min are those extreme observation values. And this is actually a one-sided test. So the null hypothesis for this test is that the maximum or the minimum observation is not different than the sample population. So if we were to try to detect an observation that's greater than the mean, then we would use this, this test statistic. And the null hypothesis would be the maximum observation is not different than the sample population. And then the alternative hypothesis then would be that the maximum observation is different than the sample population. Okay, and you may have seen these critical tables of critical values before, maybe not necessarily for the Grubbs outlier test, but for your your t-test, which I believe Dr. Armenta will discuss a little bit, and we will also talk about a little bit more later in the semester. But here, if our test statistic, and we calculated that using those equations in the previous slide, is greater than the critical value, then we reject the null hypothesis. So let's say we have a sample size of 10, and we want to see if at the alpha level of 0.05, if an observation is an outlier, it's greater than the mean, then we would move over here to the right and look at this value. And if our test statistic is greater than this value, then we would conclude that that observation is an outlier. And I should note that this test should only be used if your sample is normally distributed. Okay, so outlier tests are an iterative process. That means we would check the most extreme value first, and then we decide what to do. And sometimes we would take it out. And then now we check the next extreme value using the new smaller sample. So let's say we detect a very extreme value, we decided it's an outlier, we would take it out. Then we would look at our new sample that has that one observation removed, and then we would check for outliers in that newer, smaller sample. And then we just continue on. So that's what I mean by an iterative process. And then once you've made a decision for all outliers, then you can take that new data set with the outliers removed or somehow handled and accounted for, and then you can move forward with your analysis. Okay, and this is kind of related to everything that we have discussed so far, and something that we'll get into when we start to talk a little bit more about descriptive statistics and characterizing our data and really start actually doing that in R. So here's just an example of variables or statistics that we might, or sorry, variables that we might measure and calculate statistics for in a sample. So here, let's say this is fat, and based on the values, I don't think that's percentage body fat, but let's say down here, it's a VO2 max, right? So these are our different variables that we're measuring, and then we're just getting statistics from those variables. So here, this is our minimum value for this variable fat, our maximum value for this variable fat, and then our mean value. And then remember, when we present the mean, we most often then also present the standard deviation and that in this case is 3.46. What we don't know from this table is whether these variables are normally distributed, and so whether or not the mean is actually the appropriate statistic to report for this variable. So again, we're kind of relying on the authors of this manuscript and this table that was included in their manuscript, that they've already looked at their data in this way and have decided, okay, this variable is normally distributed in our sample, and therefore it is appropriate to present the mean and standard deviation. And then if you remember from earlier in the lecture, if that isn't the case for your sample, then what statistic would we often report? And that would be the median and probably the range and also the interquartile range. All right, so that concludes lecture 2. And on Tuesday, I will give a mini recap of everything that was covered in lectures 1 and 2. And then we'll kind of discuss ways forward, whether this is working for everybody or not. And then now what we'll do in lecture 2 after that mini recap is to start to really get familiar with our working in the console area and working in the source area and write our first script.